A simple pendulum consists of a mass m attached to a frictionless pivot by a massless cable of length L. When the mass is pulled away from its equilibrium position by some small angle theta and released, it swings back and forth. If a pen were suspended from the mass and allowed to draw on scrolling paper, the pattern would be similar but not identical to the sinusoidal pattern for simple harmonic motion. Gravity causes the back and forth rotation about the axis at P. The rotation speeds up as the particle approaches the lowest point and slows down on the upward part of the swing. The angular speed eventually reduces to zero and the particle swings back. From the rotational analog of Newton's second law of motion, a net torque is required to change the angular speed. The gravitational force mg produces this torque. Note that the tension force T rotates with the pendulum and always points at the pivot, and therefore produces no torque. The magnitude of the torque, tau, is therefore the product of the magnitude mg of the gravitational force and the lever arm L, so that tau equals negative mgl. The minus sign indicates that it is a restoring torque, much like F equals negative kx is the restoring force of a spring. The lever arm L is the perpendicular distance between the line of action of the gravitational force mg and the pivot P. For small angles, theta 10 degrees or less, the arc length S and the lever arm L are approximately equal. Since we are assuming small angles, we can say that L is approximately equal to S, which equals L times theta, for theta in radians. We can then write the torque as tau equals negative mgl, which is approximately equal to negative mgl theta, which equals negative k prime theta, where k prime is a constant equal to mgl. The equation tau equals negative k prime theta has the same form as Hooke's law. For the frequency of a spring, we had omega equals the square root of k divided by m. For the angular motion of the pendulum, we expect an equation of the same form, but with k replaced with k prime equal to mgl, and the mass replaced by the moment of inertia I. The result is omega equals 2 pi f equals the square root of mgl divided by I. Again, this result is valid for small angles only. This equation gives the frequency of any object swinging at small angles, as long as you know the moment of inertia of the object. In the case of a simple pendulum, which is just a point mass on the end of a massless string, the moment of inertia is mr squared, which in this case is equal to ml squared. If we plug that in for the moment of inertia, we obtain omega equals the square root of g divided by L. Note that the mass m no longer appears in the equation, and therefore the frequency is independent of the mass. This was not the case for the frequency of the oscillating spring, which depended on the mass. Therefore, in the case of the pendulum, the longer the string, the smaller the frequency, and the longer the period. In summary, for small angles, the frequency of oscillation of a pendulum is given by omega equals 2 pi f, which equals the square root of mgl divided by I, where L is the length and I is the moment of inertia. For the special case of a simple pendulum, which is just a point mass swinging at the end of a massless string, the frequency is given by omega equals the square root of g divided by L.